algorithms. But I think you mentioned algorithms.
So the idea is that the elementary matrices will actually help us find a way to find inverses. Oh, great. I don't have the notes up yet. Man, I'm a little behind in this class. So, do you remember the elementary matrices and what they come up with?
It's like one operation at a time.
Yeah. So one operation at a time. So here's our example from last time, and this is how we get to build up the inverse. So let me go back to our notes here. So there's three types of elementary matrices. One of them is to multiply a row by a constant. The other one, switch a couple of rows. The other one is the one that we use the most. We multiply one row and add it to another. And then here are some more ideas or facts about elementary matrices. If an elementary row operation is performed on an m by n matrix, the resulting matrix can be written as EA, where E is the elementary matrix. So that's the idea that we multiply the matrix on the left side by the elementary operation that we're talking about. And then each elementary matrix is invertible, and the inverse of that is the same type of transformation. So if we take an example of switching rows is pretty easy. Let's take the example of multiplying one row by a constant, adding to the other row. So, for example, in a 3 by 3, if we multiply, say, the first row by 2 and add it to the last row, then that elementary matrix is going to look like the identity matrix with this operation made on the identity matrix. So we're multiplying the first row by 2 and adding it to the third row. This would be 2, 0, 1. That's your elementary matrix. And if we do this to an m by n matrix, or 3 by 5, or 3 by 3, or any matrix, then you'll see that that's exactly the row operation that would happen. But I was concerned about, or I was interested in, this last bullet point over here. Each elementary matrix is invertible, and the inverse is the matrix of the same type of transformation. So if it's the same type of transformation, what can you imagine we have to do to get this back to an identity matrix? So I would probably multiply that by -2, multiply the first row by -2, and add it to the third row. And what you can do is you can multiply these two matrices to see that you are in fact going to get the identity matrix. So E multiply with E inverse 1, 0, 0, 0, 1, 0, 2, 0, 1. multiply that with 1, 0, 0, 0, 1, 0, negative 2, 0, 1. All right, so row and column, first row, first column will give you 1. First row, second column is 0. First row, third column is 0. Second row, first column is 0. Second row, second column is 1. Second row and third column is 0. Now this is the interesting one. So first row and first column. So we got 2 times 1, 0 times 0, 1 times negative 2. That turns out to be 0. And then third row, second column is 0. Third row, third column is 1. So this does check out, and you really should also multiply E inverse times E by switching the order, but we'll get the same result. So this is an example that illustrates the second bullet point here, that the inverse of an elementary matrix is another elementary matrix that is of the same category. And by category, I mean, you know, one of these 3 categories. All right, and just to re-illustrate our example from last time, I'm just going to take our notes from last time and just copy it. Say this is what we did. And we came up with the idea that this would be a way for us to find A inverse. So from last time we came up with this example where we multiplied the matrix on the left by some elementary row operations, and we see that we got exactly what we would have gotten if we did those elementary row operations the way we did. And then in the end, we stacked up all these matrices, these elementary matrices on the left side, and we said that, well, if we multiplied together, that's just A. And so, oops. Yeah, so it's these matrices over here multiplied all together that would give us our A inverse. Yeah. Well, we can come up with these things. This is not the ideal way to find the inverse of the matrix, but this is just to illustrate that these elementary row operations play a part. So, but you can come up with the operations that we did by, you know, what's one of our operations, E1. So what we did was we multiplied, this is our original matrix. We multiplied the first row by 1/2. And so to get the elementary matrix, you would multiply the first row by 1/2 of the first row of the identity matrix by 1/2. And then that's how you would get your E1 or your E2, your E3. That's how you would get elementary matrices. Right.
Transform the identity matrix into
Yeah. Yeah. So that's one way to do it, but we're not going to do it that way. We're going to do it similar to that, but we're going to keep a record of our elementary row operations. And so I will use the same example, 2, 0, 0, 0, 0, 3, and 0, 1, 6. So this is the more practical way, one of the more practical ways to find the inverse. So we'll use that matrix. What was it, 3? 0, 3, 0, 1, 6. Okay. So what we're going to do is we're going to write A and the identity matrix side by side, kind of augmented together. So we got 2, 0, 0, 0, 0, 3, 0, 1, 6. And then we'll put the identity matrix over here. And what we're going to do is we're going to go through our elementary row operations to get this in row echelon form, reduce row echelon form. That would essentially make this side into the identity matrix. We want to make that side into the identity matrix. And what we're going to do is we're going to keep, essentially by doing that, we're going to keep track of what happens to the identity matrix as we do those operations. All right? So let's do that. Let's do our steps over here. And just to be exactly the same as it was before, the first thing we actually did was we switched the second and third rows. So let's do it exactly the same way. So we'll do the switch on the second and third row on this 3 by 6 matrix, and then we'll see the progression. 1, 0, 0, and then we switch 0, 1, 6, 0, 0, 1, and 0, 0, 3, 0, 1, 0. So you can see that the switch over here, keeping track, this is now the E1 matrix that we had where we switched the order from your previous notes, also from this previous page. So this is the E1 matrix.
On the elementary method, we just did each time separately.
Yeah. Here we're just doing now.
It's the same thing, it's just we're just putting them right next to each other.
Yeah. Except in our next step, you'll see that you're not going to get E2, but you're going to get E1 or E2 times E1 altogether already. Okay. So our next step, what's our next step? According to what we did last time, our E2 was when we multiplied the first row by 1/2. So let's multiply the first row by 1/2. First row by 1/2. And then we get 1, 0, 0, 1/2, 0, 0. And everything else stays the same. And what we have here is E2 and E1 multiplied together. And then our E3 was we multiplied the third row by 1/2, our E3, by 1/3. So let's go ahead and do that. One-third times row 3, 1, 0, 0, 0, 1, 6, oops, the other one. 1/2, 0, 0, 0, 0, 1. So the last one gets multiplied by 1/3. 0, 0, 1, 0, 1/3, 0. By the way, we never really worked this out. We never figured out what the matrix was. We'll find out now. So this is elementary row, elementary 1, E2 and E3 multiplied together in reverse order, so it's E3 times E2 times E1. And I think what we want to do, if I'm just looking at this, I want to multiply the third row by -6 and add it to the second row. So multiply the third row by -6 and add it to the second row. 0, 0, 1/2, 0, 0. So this is, the third doesn't change, the third row doesn't change. Let me write that out first. So now the second row, I need to multiply this by 1/6, or by -6. So 0, 1, 0. And now the left-hand side has become the identity. And then I would multiply this by -6. So 1/3 times -6 is -2. And I would add it to the second row. So 0, -2, and 1. So this is E4 times E3 times E2 times E1, which is also A inverse. So once you get the left side of your augmented matrix to be the identity, then the resulting matrix on the right-hand side is your A inverse. Okay? So we should probably double check this by multiplying the matrices together. And it doesn't matter which order we multiply. We should do both, but I'll just do one of them. So the original matrix was 2, 0, 0, 0, 0, 3, 0, 1, 6, and the resulting A inverse that we got is 1/2, 0, 0, 0, -2, 1, 0, 1/3, 0. So we do the multiplication. First row, first column will give us a 1. First row, second column is 0. First row, third column is 0. Okay, second row times the first column is 0. Second row times the second column, that's the 3 times 1/3 is 1. And second row and third column is 0. Third row, first column is 0. Third row, second column, I have a -2, and then 6 times 1/3 is +2. -2 plus +2 is 0. And then finally you get a 1 for that last one. So that does check out. You should also check A inverse times A to make sure that it's the same thing. Okay? So that's the stuff we needed to do last time. And I said we're going to skip 2, 3, and then jump 2, 3, 2, 4, 2, 5, 2, 6, and jump up to 2, 7, or 2, 8. We're going to jump up to 2, 8. But before we do that, there is a theorem in 2, 3 that I do want to cover. I just want to post it or paste it onto our notes and talk a little bit about it. Okay? Unless there's one more piece of information here that's important. Oh, there's a theorem 2. Let me just mention this theorem. This is from 2.2. So if you have a square matrix, then it's invertible if it's equivalent to, if and only if the row equivalent, it's row equivalent to IN, which means you can do your basic elementary row operations. So in this case, any sequence of row operations reduces A to IN and transforms IN into A. So that's exactly what we did in our example. We did our A to I, and then the elementary row operations eventually got us to make the A side look like the identity, which means that they're row equivalent and then your resulting augmented portion is your inverse. So if all you do are elementary row operations, then you went from A to I, then that means they're row equivalent, which is what they're saying in the theorem. And then not only that, but you follow the same row operations on the identity matrix, you're going to get your inverse. Okay? So that's what that theorem is saying. We kind of showed that with an example. Okay. Let's jump to the theorem that I wanted to tell you about. Is it going to fit? This theorem is in 2-3. So what's important in, it turns out what's important in linear algebra is that when we want to find information about something, there's a lot of ways to get there, and that's what these equivalencies are saying, is that to say that your matrix A is invertible can also mean a lot of things. And here are about 2/3 of what we have, and then at the end of the chapter, we'll get to the other 1/3 of equivalences. So the main idea is that if something is invertible, then all these things have to follow. If any of these things are not true for the matrix, then you can say that the first statement is not true. So these are called if and only if statements, which is to say that either all of them are true or all of them are false. You can't have one statement to be true and the other one to be false. Okay, they all have to have the same truth to them. So this is saying if it's invertible, then A is row equivalent to the identity matrix, which is what our last theorem said. And our last theorem also says that if it's equivalent to an identity matrix, then it's invertible. So other ways to check for invertible is that if it has n pivot points. Remember, we're starting off with a square matrix, so that if they all have pivot points, then you can essentially reduce to the identity matrix, right? So that also makes sense. This only has one trivial solution. If we don't have any free variables, then you only get one trivial solution for a square matrix. If you have free variables, then that means it's not invertible. The columns form a linearly independent set. So if you know that piece of information already, then you can just say, okay, we know that the matrix is invertible. Now, you might still have to find it, but you know that it's invertible. Also, linear transformation is 1-to-1. The equation has at least one solution for B in Rn. Somewhere along the line here, the linear transformation is onto. So if you have an invertible matrix, then that linear transformation is 1-to-1 and onto. So you can kind of package these two together, the 1-to-1 and onto business. So there's a matrix C such that CA is equal to the identity element. And all this is saying is that, oh, you can just solve for A by multiplying by the identity. So C is equal to A inverse. And the idea is that since it's not commutative, we have to be able to account for this idea from the left and from the right side. So in this case, D is also your inverse matrix. And it turns out that if it's invertible, then it's transposed. It's also invertible. And we translate everything from columns to rows, and then all the rows must be independent and all that other stuff. Okay. So this is a big equivalence theorem that says a bunch of these things are equivalent statements to each other. And like I said, this is about two-thirds of them, and there's still going to be a handful that we're going to add on to this when we get to chapter or section 2.9, 2.8, 2.9. I think it's 2.9, the last one. Okay. Any questions? All right. Let's see. Is there something else? One more piece of information from section 2.3. If we translate all this information to linear transformations, matrices are essentially linear transformations, right? Or if you have a linear transformation, you can write it as a matrix. So if you have a linear transformation, that's invertible. So this is saying the same thing with inverses, with transformations and inverse matrices. It says that if you take the composition between S and T in either order, then you should get the original thing, the original vector that you put in. So this kind of should remind you of f of x back in pre-calculus, and g of x equals ln x. Just as an example, if we do the composition of these two things, f of g of x, what's that? That's e to the g of x goes inside ln x. This is equal to x. And that also is equal to g of f of x, which is the ln of e to the x, and that's also equal to x. So this is essentially saying the same thing. So if T is a linear transformation, and let A, B be standard matrix for T, then T is invertible if and only if A is invertible also. So this gives a relationship between matrices and linear transformations. And that S vector, or that S function transformation that they gave, is actually A inverse. This is equation 1 and equation 2. Yes? No. Yeah, you lose information. Remember, projections not one-to-one, right? Because you got several points going to the same point. Yeah, so you lose information, and because it's not one-to-one, it's not invertible. Rotations are, yeah. So projections, I don't know if this is an example for this. Projections are not invertible because they are not one-to-one. Maybe this comment would have been good on the previous page when we were talking about this thing being one-to-one. So maybe I'll just put it there. Not linearly independent, they're not going to be invertible. So if you have column vectors that are not linearly independent, then it doesn't work. Oops. Yeah. Okay. All right. So let's now do a quick leap to 2.8, where we're talking about subspaces. And unfortunately, we didn't get to talk too much about this whole idea of what we're doing. All those vectors that we're talking about, they all live in this thing called a vector space. So we didn't get to talk much about vector spaces, which is kind of too bad. But the subspace means it's a space of under a vector space.
So vectors exist in vector spaces?
Yeah, vectors exist in vector spaces. The other thing is that, I don't know if you would find this weird, but the set of functions, continuous functions, are all vectors also. And if you look at the whole set of functions, that could be considered as a vector space. Well, we're not talking about that, so we won't go there. But vectors aren't the only things that can form a vector space, is what I'm saying. They do follow a certain number of rules, and the rules are essentially the same rules that you would see here in the subspaces. So a subspace of Rn is any set H in Rn that has three properties. The zero vector is part of that. If U and V are vectors in the subspace, then the sum is going to have to be part of the subspace. And then if you have a vector U in the subspace, then the scalar multiple of that is also going to be in the subspace. So being that we're dealing with vectors, it kind of seems natural that we're talking about vector spaces, and it would be kind of easy to visualize. An example that they had is a picture in R3, but we can go R2 or R3. Any preferences? You guys want to?
One question. This is any set H, or just any subspace?
So H is the name of the subset, and then to show that this is a subset, to show that this subset is actually a subspace, then they have to satisfy these conditions. Let's go in 2 dimensions, and let's take a look at the subspaces of R2. Just because it's easy to visualize, and we can form sets and stuff like that. So
the set is like more than one thing.
Or it could be one thing. Yeah. So let's consider R2. Let's let H equal just a 0 vector. Is this a subspace? It contains 0, so A is satisfied. Let's check what's going on here. So is this a subspace? We have to check for all these 3 points. So 0 vector is an H. Now, the second one assumes that you have other vectors in there, that if you have other vectors, you can add them up, and they would still be an H. But you only have 0 in there, so 0 vector plus a 0 vector is equal to 0. So no other vectors. I'll say no other vectors. So this is also satisfied. So we got check on A and B, and then C. This is the only vector we have, so if we scalar multiply it, if we multiply this by 0 by any scalar, it's still going to be 0, which is still c times 0 is equal to 0. So that still works. So our 0 vector, if that's the only thing in our set, our 0 vector is a subspace. So that's good, I guess. Now let's find a different H. And we're talking about R2, so we can just look at a plane and imagine a subspace, a subset. So what if we look at the first quadrant, and let's include the axes. So one way to write that is we can say first quadrant including the axes, or we can say the points x and y such that x is bigger than or equal to 0 and y is bigger than or equal to 0. Is that a good description for the first quadrant, including the axes? All right. So A is 0, the 0 vector in H. If we include the axes, then yeah, it's going to be there. If we didn't include the axes, then that wouldn't have been there, and so it wouldn't have been a subspace. So this checks out. Now let's take B. Let's take two random vectors, and I'm going to randomly select no. So this is something that you have to, I'm just checking randomly like this.
Okay. You could take vectors that aren't.
Right, that would satisfy. Well, but the thing is you have to pick vectors that are in the space or in the set. And then you want to check if the sum of those vectors. So they wouldn't give you vectors. We're just kind of randomly choosing. So I have a vector 0, 1, or this is 1, 0, sorry, and then a vector 1, 1. So if we add those two, uh, 1, 1 plus 1, 0, and this is equal to 2, 1. Is that going to be in the space? So that seems like it works out.
You pick vectors that are in the space, then adding them will be in the space.
Yeah.
Since there's no limit to x or y, like 1 to 0.
Yeah, so x2, y2 is equal to x1 plus y1, oh, x1 plus x2, sorry, comma, y1 plus y2. And if they're all x1, x2, y1, y2, if all these are bigger than 0 or equal to 0, then the sum of these would also be bigger than or equal to 0. Then x1 plus x2 and y1 plus y2 are bigger than 0. So that checks out also. So this looks like it's got the making for subspace. Let's check the last one. C is a scalar. Ooh. C is a scalar means it should be allowed to be negative. So there we have a problem. If C is less than 0, then C times the vector xy is not in H. So it looks like we ran into an example now where it's not a subspace. We can include quadrant 3 and make it a subspace. Yeah, I don't know. I don't think you could. Why? Yeah.
That's why I created zero. All the other conditions.
The thing is that if you have a vector here, and then you add a vector that goes like that, then you might be in here somewhere.
It doesn't say, it only says scalars in a single.
That's part C, but part B says.
That's if you add two different scalars.
No, but this is part B. If I have a vector in the first quadrant, and I have another vector in a third quadrant, and if you add it, you probably won't be there. Yeah? So,
Subspace will consist either solely of the origin, be a straight line, or encompass all of
in R2. So, back to Alex's comment. These two, I've seen this in several formats, and I've usually seen these two statements put together. And these two can actually be put together, and to say that alpha u plus beta v, where alpha and beta are scalars, should also be in H. So what is this? This is a linear combination. Any linear combination of two vectors in your set should also be in your set. And this turns out to be the span of these two vectors. Okay? So let's translate that to now what Evan said. There seems to be only three possibilities in R2. Three possible subspaces in R2. One of the subspaces we actually found, if your subspace is just the zero vector. The other subspace is kind of another, I don't want to say degenerate, but another trivial subspace. So if H is equal to all of R2, then it should satisfy all the conditions, right? We got 0 is in R2. And let's put B and C together. If you have any UV in R2, then any linear combination of those vectors is also going to be in R2. And so that satisfies B and C conditions together. And that makes sense because we're in R2. We're not going to go beyond R2. So we're talking about everything in there. So that is everything in there. And if you have the span of two linearly independent vectors in R2, then that's going to cover the whole plane. So now there's one more example of a subspace in R2 that's not just that one point or everything. And that's going to be a line. And that line, there's one specific thing that we need from that line. What is that? Well, not one specific. There's one specific criteria that we need to satisfy for that line. It has to pass through 0, 0, right? You guys were all thinking that. I just didn't state my question correctly. So the only non-trivial example in R2 would be a line that passes through the origin. So the y-intercept is equal to 0. If you have a vector that goes through this point, so first of all, it goes through the origin, so the first one is satisfied. 0 is an h. Now, if we have a vector, if u would have to equal to like 1 comma m or something like that, right? Something like that. And if you had another vector that was on this line, then it has to satisfy this equation. So when x is equal to 2, for example, y is going to equal to 2m. And already you can see the third criteria saying that, you know, there are scalar multiples of each other. So u plus v is equal to 3 comma 3m, and that's also on the line. And then same with c. If you have any point on that line and then you scalar multiply it in either direction, positive or negative, it's still going to be on that line. So all these three conditions are satisfied. Okay? Now, in R3, it's almost the same. And without going through the examples in detail, subspaces are just the origin, so the 0 vector, so that would be 0, 0, 0. The other non-trivial, or the other trivial subspace is all of R3. And then there's two more. One of them would be a three-dimensional line that goes through the origin, and you can imagine that line is being spanned by one vector. And then the last one would be a plane passing through the origin. And this one, if you can imagine, it would be spanned by two vectors. And if you have three linearly independent vectors in R3, then that would span the whole thing, the whole space. So we can make that comment here also. This is spanned by three vectors. And let's just assume that when I'm saying spanned by one vector, two vectors, or three vectors, that they're all linearly independent. Okay? So this is something good to think about, because when we're talking about being spanned by one or two or three vectors, that's going to we're going to be able to talk about the dimension. So R3 spanned by 3 vectors in 3-dimensional space. A plane spanned by 2 vectors is a 2-dimensional space. And then a line spanned by 1 vector is a 1-dimensional space.
The only subspace of Rn that describes an n-dimensional object is all of Rn.
Yes, because it would be spanned by n linearly independent vectors. And then you'll have linear subspaces, planes, 4-dimensional, 5-dimensional planes, depending on what your dimension is. As long as you can essentially write it as a span of these linearly independent vectors. Yeah.
And H is a set of what?
Pardon me?
What is H a set of?
H is a set that contains, well, these are the 4 examples that we have. H is just 0, the 0 vector.
I mean, but even more generally, like we're saying, H is a set of points, but
A set of vectors.
set of vectors.
Yeah. And generally, when you look at these things, I mean, I write them as points, but I mean them as vectors. So if we can associate points and vectors, then we can, have this discussion flow a little bit easier so that we can take the visual. I mean, we can write vectors for all of them if we want, but sometimes it might be just slightly easier to consider it as a point.
Point implies to be vector.
Yeah, if it's a point, then it's a vector from the origin anyways, right? Okay. So that's the definition of subspaces. Turns out those columns turns out that anything spanned by vectors is a subspace. Let's start with a column space. So the column space of a matrix A is the set of all linear combinations of the columns of A. So it's written as this: COL for columns. Yeah, so if you have I think this is supposed to be M column space M by N matrix, subspace of Rm. So let's take a look at an example. A equals 1, 2, 3, 4, 5, 6, 7, 8, 9, -1, -2, -3. So column of A, call A equals the span of these, well, there's 4 columns, so it's a span of these 4 columns. 1, 5, 9, 2, 6, -1, 3, 7, -2, 4, 8, -3. So I mentioned that it's spanned by vectors, that however many vectors it's spanned by is the dimension. I don't think that's true. So I said something else. There's an important phrase in there. that would make that statement true. So, in other words, there's 4 vectors here, but my column space is not going to be a 4-dimensional vector space. Okay? So what has to be true for these statements that I was mentioning? Yeah? They have to be linearly independent. So spanned by 3 linearly independent vectors, spanned by 1, well, there's 1. Spanned by 2 linearly independent vectors. So can 4 of these vectors be linearly independent? Because so it's in R3. So this column space is a subset of R3. And then the most linearly independent vectors you can have in R3 is 3. So that means these are not linearly independent. Now this might end up being 3-dimensional. 3 of them might be linearly independent, and then the 4th one is not. Or it could just be 2 of them are linearly independent. So that's something that we might have to check. And what we could do is we could do the row reduction and see how many pivot points we're going to have, or how many free variables we're going to have, and then we can determine what 2 or 3 vectors would make this linearly independent. But it has to match the number of rows. The space that you're in has to match the number of rows. So this is a subspace in Rm. So that's a column space. Okay? So column space is the span of the columns. Now there's another important space called the null space. And column space and null space kind of go hand in hand. The null space of a matrix A is written as NUL. You could actually just write NULL, but they write it as NUL to keep this 3 letters. Of all the solutions of the homogeneous equation AX is equal to 0. All right, so the null space, in words, let's see if we can say this in words. So all the solutions of the homogeneous solution, so all the x's, basically all x vectors that get sent to 0. So the null space would be the set of all vectors that get sent to 0. And that also is a subspace. Okay? I think there is an example. I don't know if there's an example in the notes here.
And so when you say it gets sent to 0, you mean
when it's applied to A, or when A is applied to it. Yeah.
0 is in null A?
0 is in null A. Wait, what?
With all x.
So all x that gets sent to 0. So
All x that gets, all vector x that gets set to 0
is the null space.
is in the space.
Yeah. Oh, the null space is that.
Null space is all x that.
All x values that get sent to 0. Do you have the PowerPoints?
Oh, yeah.
Can I see the example that they have?
Sure. So it starts. I don't know.
With some more, an actual matrix. No?
You don't have anything. You go higher if you want. So just call A. This
Okay, so this is good.
this does say call
All right. Can you read that to me?
Sure. Example 4. A equals to
Or row across?
1, -3, -4,
Mm-hmm.
-4, 6, 2, -3, 7, 6.
Okay. We don't need the B. Yeah. So the column space would be the span of these things, these three vectors, right? Now, we don't know if these vectors are linearly independent or not, so we can row reduce it and see what happens. Anyway, so let's go through the row reduction process and let's see what happens. Actually, let's do that in the spirit of solving for AX equals 0. So essentially, let's find a null space. So let's see if we can find a null space. We want to find all x vectors that get sent to 0. That's what we're solving for. Let's see. Let me rewrite this over. 1 minus 3, -4, -4, 6, 2, -3, 7, 6. And -2. All right. Damn it. Can you just tell me the reduced answer in your notes, Brian?
Oh, for that, whatever it says?
Yeah. They have the answer on the next slide.
That's B?
No, not the vector B, but the A reduced without the vector. Down here. Yeah.
This thing?
Yeah.
1, -3, -4, 3.
I don't need that third.
I don't need that column. 0, -6, -18, all 0.
So after you do some row reduction, this is what you get. This is our row echelon form. It's not quite reduced row echelon, but we can see that we have a pivot in the first and second columns, but none on the third. And so we have a free variable here, right? So if we take it from here and we say x3 is free, and then you say x2 is equal to, what is it, 18. So 3x3, positive, negative. It's negative. And then x1 is equal to positive 4x3, positive 3x2. Negative 5x3. So then we can essentially write our x solutions for this to be x3 times -5 for x1 for x2 is -3, and this is just being multiplied by 1. So this is our null space. Null space is spanned by -5, -3, and 1. So this is our null space. We've done these solutions before, right? When we're solving for homogeneous systems, and we're comfortable. We should be comfortable writing it like this. And so what we have here is one vector that's being multiplied by a scalar, so that vector is spanned by that scalar. When x3 is equal to 0, you're at 0, and any scalar multiple would be just on a particular line in 3 dimensions. So the null space in this case would be this, a line spanned by this vector. And we'll see that the column space will probably be a 2-dimensional vector, or a 2-dimensional subspace spanned by 2. All right? All right, so we're a little bit over because I was looking at that clock over there, which is a little bit slower. But this is the halfway, we're halfway through 2.8.